So yeah, I'm Wynn. I'm a graduate student at Northwestern. And today I just wanted to share with you this really panchromatic study of a very nearby calcium-rich transient that was observed last year through this year, and just how our observations across the EM spectrum were just an amazing probe of mass loss, of the progenitor of calcium-rich transients, and just the explosion mechanisms that power these really rare, interesting subluminous transients. All right, so I just like to start with a pretty image. This is M100. It's at 16 megaparsecs. It's in the Messier group. And right here is the topic of this talk. This is calcium-rich supernova 2019 EHK. This is the closest, so most nearby calcium-rich transient we know of as of now. And the proximity to us is actually one of the most powerful things and mechanisms in this study. And also the fact that, as you can see right there, it was observed only 10 hours after explosion. So in supernova science and transient science, that's an amazing probe of the final moments of stellar instability right before an explosion happens in any transient, and especially for something as rare as a calcium-rich transient. But before I get into the study, I just wanted to kind of backtrack a little bit for those who aren't familiar with the calcium-rich transient class, and just define a couple of things before we move forward about what makes something calcium-rich and why we even care about this interesting, weird class of supernovae. So calcium-rich transients are in this kind of luminosity gap. So they're a little bit lower luminosity than typical supernovae. They're more luminous than a typical novae. As you see in this light curve, they're all kind of falling relatively quickly, and they peak around -16 mag in R band, and they rise relatively quickly. So in terms of the explosion mechanisms, that just indicates that they produce pretty small amounts of ejecta and also synthesize relatively small amounts of nickel 56, which then gives us like underluminous or subluminous luminosity. Spectroscopically, they rarely show hydrogen, if at all, and so it's a normal type 1 spectrum, shows some helium photospheric lines. Their velocities are kind of in the range of a normal thermonuclear transient, so just to keep that physical picture in mind as we go forward. And the name calcium-rich transient actually comes from this feature right here. So if you see on the right, you can see these forbidden calcium lines superimposed on the forbidden oxygen line. So these are nebular transitions in the nebular spectrum of calcium-rich transient. And as you can tell, the forbidden calcium line is way larger than the forbidden oxygen line. And essentially, the name calcium-rich transient is no more than just an observational tag, which means that if we observe these things out to nebular times, we see that the supernova itself is choosing to cool predominantly through calcium-2 over oxygen-2. And obviously the reverse of that would be a normal type 2 spectrum, type 2 supernovae from some sort of massive star that chooses normally to cool through oxygen, because there's just that much more oxygen around for the supernova to cool down in. So keeping in mind, that's what makes something calcium-rich. And one more kind of defining trait is that we typically in the past have observed them in outskirts of elliptical galaxies, but maybe what I'll convince you of today is that they're really kind of an amalgam of events, and they occur all over the place. So it's really interesting to understand host environments now that we're picking up more of these objects in our sample. Yeah. Okay, so going on to the actual topic of today's talk, 2019 EHK. So the title of the talk says DoublePeaked light curve. What that means is that there's actually a physical double peak in this light curve. So centered at 0 days is actually where the normal supernova would just be peaking because of nickel-powered radioactive decay. But what we can see right here is this kind of weird primary feature, which is this excess of flux that doesn't really correspond to the normal supernova mechanism. So what we need, even before we start into this journey of what is 19HK, where did it come from, we're already seeing just in its optical emission that we're seeing this excess of flux that needs to come from an additional explosion mechanism or additional physical mechanism in the supernova that is different than just the synthesized nickel that typically powers a normal supernova light curve. And for those who are familiar with double peak light curves, there's a couple ways that theorists think that this could actually occur. And one way that maybe I'll just put in your mind, and then once we get to a physical model that will come up later, is that the primary peak can occur from this shock cooling of an extended envelope or sustained interaction with some sort of circumstellar material right in the local environment of the calcium-rich of the supernova. In this case, the calcium-rich transient 2019 EHK. So moving on to the spectroscopic evolution, because it was so nearby, it was observed very young. So this is the classification spectrum, and as you can see, it's pretty featureless, besides these really amazing features right here and here. And what these are flash-ionized lines from a circumstellar material, so H-alpha, helium-2, and what this really represents is that right after shock breakout, the shock propagated into this shell of circumstellar material. The material recombined and produced these really narrow emission lines that essentially showed us for the first time that calcium-rich transients, the progenitors of calcium-rich transients, lose a certain amount of material in mass loss prior to explosion. And if we probe them early enough, we can actually see signatures of the progenitors, like turbulent mass loss right before explosion. So what this showed was that there's actually this was the first evidence that calcium-rich transients can have some sort of CSM around their progenitor star at the time of explosion. And maybe this is already kind of connecting with what I already said about the optical double-peak light curve, because that kind of, how do you get excess flux in any sort of transient? You have this extra material surrounding the progenitor star when it explodes. So this is already piecing together, this is already starting to make a really nice picture of where this transient could have come from. But this is just a novel observations that we had just never thought could occur in a calcium-rich transient. So moving on to just the full spectral sequence, just to give you an idea of what this transient looked like over its full spectroscopic evolution. I showed these flash-ionized lines. That gives an indication of how fast the circumstellar material is moving at the time of explosion, at the time of shock breakout. I told you that this is a calcium-rich transient. So as you can see, there's already the emergence of this forbidden calcium feature here and also here. So by nebular times, we are seeing that this supernova is predominantly cooling through the calcium-2 line transition, indicating that there's just that little extra bit of calcium around that nature has decided subatomically to cool through. And one more thing I just want to highlight is that there's also these really persistent helium lines if we look out into the IR. And that just indicates that there's not only helium that I showed from the first spectrum in the circumstellar environment, but the star that exploded that produced 19HK had some helium on its surface. So we need to reconcile that as we start to think about what could have caused the supernova 2019HK, but what progenitor could have existed prior to that supernova. So that's that. I wanted to kind of put the optical sequence next to each other to give you an idea about how this supernova evolved in real time. So this is the first spectrum at 1.5 days. This is what I showed you as a classification spectrum. On the right is a bolometric light curve. And I'll just start this. This is a little time sequence movie. So relatively featureless continuum. As it's rising to its first light curve peak, it falls off. So the rise and fall in flux, there has to be some mechanism for that. Out to 10 days, we're already starting to see this emergence of really prominent calcium absorption, which then will turn into this forbidden line transition as it starts to cool down. We reach its primary peak around 14 days, so that rose relatively quickly. That kind of fits into the calcium-rich transient class. The supernova falls off, and as maybe you'll see on the spectral sequence, it's really starting to be dominated by calcium, forbidden calcium, and the regular calcium-2 line transition, which is typical of these transients and makes this object fit really nicely into the class. And by the end of 270 days or so, this is just predominantly a calcium-rich supernova. So optical emission is not all that we studied with 19HK. 19HK actually represents the first calcium-rich transient with an X-ray detection. So there are some high energy parts of this talk. It's not all just optical and low energy stuff. So as you can see right here, Swift-XRT observed 19HK within 3 and 4 days after explosion and saw this really bright, quickly fading X-ray emission, which I'm just going to say a lot of firsts in this talk. We just did not know that calcium-rich transients could produce X-ray emission, but we also had never observed them this early after explosion or in such close proximity. So there's a couple different things that we need to reconcile there if we're going to start seeing more X-ray emission from calcium-rich transients. But just looking physically at what this means, the X-ray emission means that there is, and short-lived X-ray emission, I'll say, is that there is this nice compact shell of CSM, which we already explained from the flash-ionized lines makes sense, that there's this kind of nice compact shell of CSM that was, that the shock propagated through, passed through, induced this X-ray emission, and then quickly faded because this shell of material is just very compact, very confined around the progenitor star of 19HK. So this is really powerful, and it's a really nice probe because we've now essentially said 3 things that work really well. A double peak light curve that indicates some excess material that needs to be shocked and power the light curve, flash ionized lines that give us the material's composition that's in the circumstellar environment, and now X-rays, which give us the density and the extent of circumstellar material that we just had never known existed around the progenitor of a calcium-rich transient. So moving on to the final piece of the panchromatic study, radio emission. So we were not as fortunate with radio observations as we were with X-rays because we just did not get on target early enough. So you can see right here, we essentially just have really deep non-detections for 19HK after 30 days after explosion. So while it would have been really fascinating to get on target as early as 3 days with the radio telescope, non-detections at such late times tell us how what the shock is seeing at further distances away from the progenitor star. So 10 to the 16, 10 to the 17 centimeters, we can infer some mass loss rates that are pretty low. So that needs to work into our models when we start to think about what progenitor could have produced this star. And we're also starting to we can also use the radio non-detections to kind of constrain other strange models or more exotic scenarios like some sort of off-axis jet or tidal disruption. This just wouldn't be sustained out to late times. We should be seeing some sort of substantial radio emission if this were the case. Lastly, another really fascinating piece of this puzzle is that 19HK, like I said, exists in a really local galaxy, M100. M100 is a really nice target for HST, for Spitzer, for Chandra. So they've been observing this for over 2 decades now. And so if we look at the explosion image in HST, just to give you a reference idea about what this looks like, this is the supernova. And 2 decades prior, we can look right at the explosion site, at the site of 2019 EHK, and see if there's anything there in many, many bands of HST, Spitzer, and Chandra, and we see that there's no source detected. So while it would have been amazing to find the actual progenitor of a calcium-rich transient in pre-explosion imaging, not seeing a source is actually just as fascinating because we get to constrain what could have been there and what stars are excluded as the progenitors of 19HK and of calcium-rich transients in general. So I'm running a little bit low on time, but I'll just explain this HR diagram really quick and what we can rule out. So in the blue to kind of purple regions is where the progenitor of 19HK could have been and also been hidden from sight. And what we can see really nicely is that single massive stars are just not really acceptable progenitors for 19HK and for calcium-rich transients. And if we look at the HR diagram for binary stars, the same kind of exists. We really need to only have low mass stars, so massive stars in the low mass bins, or binary stars, or some sort of white dwarf binary. So compact stars really seem to be the nicest progenitor and works the best with these pre-explosion constraints. So I already said that there needs to be some physical model that reproduces 3 key signatures in 19HK. And so that's a double peak light curve, flash-ionized helium spectral lines, and luminous X-ray emission. I think that's the 3 most constraining things on what was the progenitor of 19HK. And so let's just start with a really simple toy model about what could have been the explosion mechanism and the star system responsible for 19HK. So I'll start with some sort of compact progenitor. I'm not showing the binary. I got a lot of questions about, wait, where's the binary? You just said this is probably from a binary system. Let's just focus in on the compact star that probably exploded to produce 19HK. We know that we need to produce this double light curve peak, this first light curve peak. So we need some sort of material that can power excess flux above the normal supernova continuum. So if we model that, 1 minute?
Yeah.
Okay, I think I can get through this. Okay, so extended envelope, we can model that to produce that excess emission. We also know from the X-rays that there's this CSM, this confined CSM around the star in the local environment. We know its speed, its composition. We know how far away it is in its mass. And right after shock breakout, this shock will slam into the CSM. It will induce some optical emission, not only from the cooling envelope, but also from the CSM being having kinetic energy continuously transferred throughout it. That will induce some X-ray emission. That works. We're also going to see recombination lines because the shock has propagated right into a helium and hydrogen-rich CSM. And we'll also get secondary optical emission. And if we look at the light curve, the first light curve peak, this works really well. So we get fading cooling envelope emission and CSM interaction emission, and then rising and fading CSM emission that could power this first light curve peak. So this physical model works pretty well. And I think it's a really nice picture for a calcium-rich transient that we just had not put together as of yet because we've never observed something so young. So just zooming in a little bit, just to recap, 19HK is an M100 that's really nearby. It had the first signatures of Xray emission, of shock-ionized spectral features. It had a double-peaked light curve that was probably from shock cooling or shock interaction with the local CSM or an extended envelope. And the optical emission and across the spectrum really gave us a nice picture of where this transient came from. And pre-explosion imaging was able to tell us what progenitor stars could have produced this object and what progenitor stars were not allowed. So just to recap really quick, yeah, that's essentially what I said already. Calcium-rich supernovae are really going to be fascinating if we can observe them in high energy in X-rays. And yeah, I'll take questions.
All right. Thanks very much. And so questions for Wynn, we have time for one or two. Our first question is from Sarah Markov, and she said that supernovae exploding into the surrounding CSM has been invoked in the past as a way to crank up cosmic ray acceleration. Is there any evidence for gamma ray emission from, for example, Fermi?
I know that Fermi was not looking at the source, so there's no indication of that. But that would be a really, really fascinating thing to look at if we had something local, like 19HE again. So yeah, unfortunately not.
And Brian Greffenstedt asks, could you estimate a horizon where Swift-XRT is capable of seeing the early emission? This one's obviously close by. How far out might we be able to see something like this?
Yeah, so we thought about this a little bit. Obviously, with something more powerful like Chandra, we can extend that horizon a little bit more. But I think with Swift-XRT, for the X-ray emission that we saw, it's at 50 megaparsecs is kind of the best regime. I think I'm not positive if that's the exact horizon, but I'm remembering about 50 megaparsecs.
Thanks. One last question is, you mentioned this, your preferred model might be that this is a compact progenitor. Can you think of any other observations that would help you distinguish between a compact progenitor and, for example, a lower mass, high mass star?
Yeah, I think, deeper pre-explosion imaging would have been great. Probably more earlier time radio emission would have been interesting to explain some pre-explosion models. But yeah, I really think that it's less observations and more just additional modeling in theory, because a lot of people have had really nice ideas about how this could work from both white dwarf systems and also massive stars like stripped envelope, supernovae, progenitors. But the biggest problem I have is just you need to keep some local hydrogen and helium in the CSM, and sometimes that's really hard with a low mass massive star. If you have some sort of companion that's stripping things. So honestly, I would say almost I would prefer more theorists and more models. I think this had a lot of observations that told us a lot.